Let's review calculator procedures with one massive problem. The velocity of a particle that is traveling along the x-axis, so back and forth in a horizontal fashion, is given by the function below. At time t equals 0, the particle is at x equals -3. Whenever they tell you something like that, you'll probably need it later, maybe not initially. So find every t value where the particle changes direction. The particle changes direction when the velocity changes signs. So that's going to happen at x-intercepts. Not every x-intercept, however, is a place where you change direction, because you could have a situation where you're bouncing off the x-axis. Okay, so we're going to be using the calculator. I'll try to get it to where there's not a glare here. And the importance of this problem really does have to do with, well, calculator procedures. So let's type the function in. We're going to go into y1. And we are, of course, in regular function mode. Nothing too crazy, no polar, no parametric, none of that stuff. It's in BC calculus, okay? And instead of t's, we'll put x's, but that's all right. And I want to know where the particle changes direction on the interval from 0 to 2. So here's the first little calculator trick. We're going to go on the window from whatever it is. It doesn't matter what it's set on right now, but we're going to go from 0 to 2 for our x values, 0 to 2. And I am going to let the calculator adjust the y values for me by pressing zoom. And it is option 0, and that is zoom fit. You could just press 0, but what this does is it adjusts the y values based on the x values that you've already given it. And we've adjusted the x values to go from 0 to 2. We will press enter, and we're about to get a lovely graph from 0 to 2, and I want to know every t value where the particle changes direction, and that happens here, and it looks like here we'll deal with that one a little bit more in just a moment. So let's find this one. So here's calculator tip number 2. We're going to find zeros, second and calc, and takes us to 0. This one is very familiar. Let's go to the left of it. I'll tell you what, let's just type the number 0. We could move the arrow, or we could just go 0, because I know 0 is to the left of that. And right bound, let's just go 1, 0 to 1. Sometimes you can just type like that. And we're stuck in between 0 and 1. We'll press enter for a guess, and it gives us one of those values. We'll go ahead and write that down. So t equals 0.393. There's one of them. Here's another one. We're going to do some fancy zooming over here to figure that one out. It's going to be a good little way of doing it. Second and calc, we're going to calculate another 0. Left bound, we can use the arrows again if we want to. I think I am this time. We are to the left of that x value. We're going to go to the right of that x value, which happens to be above it. And we'll press enter. And here's another one. So 1.178. 1.178, and then there's some other fantasticness that happens here, and we can't quite see it. So I think we can adjust this a little bit. So I'm going to do something I seldom do, but I kind of like it. So I'm going to do what's called a zoom box. If I press zoom, I can go to a zoom box. It's option number 1. And I want to get right around this little thing, and I'm going to basically take this tiny, tiny little window here. Notice how I've got my fingers close together, but I want to go this way. So where my fingers are, these are the 4 corners, and we're going to stretch it out. You'll see what I mean. I'm slightly above the x-axis right now. I'm going to press enter, and as I move, what I'm doing actually is creating a new window, and I press enter, and here we go. This is going to give me that x-intercept that was in question there. There it is. That's it. That's a sneaky one. So we're going to find that one as well. So second and calc, 0. Left bound, we are to the left of the x-intercept. And we'll go let's just press 2. We go all the way there, and we press enter. And 1.96, that is very close to 2. 1.963. Yeah, there we go. So I had briefly said something earlier, and in the context of this problem, it's good to know this. Find every t value where the particle changes direction. And again, that was everywhere we crossed the x-axis, went from positive to negative or negative to positive. And if we were going to just simply bounce off the x-axis and never went below it, or bounce off from below and never went above, then technically we did not change directions. So that didn't happen in this situation, but it's good to know. Okay, let's move on to part B. I want to find the average velocity of the particle on the interval from 0 to 2. Well, the average velocity is, well, the average value of a function. It sounds like we're dealing with slope, and we sort of are. They already gave us that slope, that rate of change, the velocity. So the formula we're going to use in this case, I'll write it in green, is the integral from A to B of our, in this case, velocity function. I'm going to call it f of x. This is just the generic formula. This would give us the area, but if we divided by the width of the interval, there we go, then we would have the average value of that function. So this is what we're dealing with. Of course, we're dealing with it with velocity and time and 0 to 2 and all that. So what we're going to figure out instead, I'm switching colors here, is the average velocity, and again, velocity is the function they gave us, from 0 to 2 of v of t dt, and we can just simply type that in the calculator, and we're going to. So I don't need the graph for this one. Let me slide over here so there's not as much of a glare. If I could get this moved just right. There we go. Y equals, and we have the function in there. So let's see. I need 1/2 times math, and it's the integral, 9, from 0 to 2 of our function, and here's how we retrieve a function. It's alpha and trace. It's like the F4 on my calculator. It's that little green F4. And the velocity function is y1. And we are dealing with, on paper, it's the t variable. On the calculator, it's the x variable. And this will tell us the average velocity, and that is a very small number that is ridiculously close to 0. But I'm going to use, consistent with what we do, well, let's use the correct color here. I'm going to use 3 decimal places, 0.002. Go further if you like. Find the total distance that the particle travels. Okay, now things change just a little bit. If I want to know the total distance the particle travels on the interval from 0 to 2, then I need to think about where my velocity was positive, where my velocity was negative. So I'm going to readjust my window. We're going back to the same concept from part A, where I adjust my window from 0 to 2. My last window was that zoom box where we pinched it over in the corner and stretched it out. So we are going to readjust this from 0 to 2, and again, I'm going to go zoom, and option 0, don't scroll, just press a 0, but I just wanted to show it to you. And it takes it a minute because it has to calculate what's the highest, what's the lowest, so it'll know how to do its interval, the y interval. The total distance a particle travels, well, from a calculus point of view, looking at it at the graph, since we're looking at the velocity, that would be this area plus this area plus this area, and plus there's a itty bitty piece down here that we don't see because we had to zoom in to see. There's a tiny little piece under there that is also negative. So basically we would have this area plus this area plus this area plus this tiny area down here that we don't see. And the way it would calculate in the calculator is positive, negative, but we want the total distance, meaning particle moves forward, we count it forward, particle moves backward, we're going to still count it positive, which means we're going to need to do the integral from 0 to 2 of the velocity, absolute valued, that's going to make everything positive, dt. So here goes, we're going to do it. Let's quit, second and quit. Let's not quit the problem. Let's just quit that graph for now. And we are going to find an integral, so math 9 from 0 to 2. And we will find the absolute value. You will find absolute value under the math menu. We're going to go over to number. There's numbers. There's several different things under the math menu. It's amazing. There's probability. There's all kinds of fantastic stuff. But right now we're going to go to number, which is where we find a lot of more just basic numerical things. Absolute value. Press enter on abs. And we need the v of t, which we have stored as y1. Again, that's alpha and trace. That's the F4, y1. And we're using, whoops, wrong place. We're using the x variable. There we go. This will tell us the total distance that we've traveled. Takes it a minute. There's a lot of ridiculously hard computations to do. we'll put that decimal there. All right, what is the position of the particle? Oh, okay, time t equals 2. So this is where things change a little bit conceptually, and there's not going to be much difference in terms of calculator tricks on this one, but we do need to review it. So here we go. The position of the particle at time t equals 2. Well, time t equals 2, what that means is, let's just start at time t equals 0. We start at 0, and when we start at 0, the particle is at x equals -3. So there's this horizontal number line, 0, -3. And it starts here, and then it moves forward and backward and all kinds of stuff. But it started here. So we're going to start at our starting point. And so that is going to be, well, -3. And then plus. Well, how far did we travel? Okay, that's actually not the question. Let me rephrase that. What's our displacement? This is how far we traveled total. That is our total distance that we traveled. But what I really need is the displacement. I need to know when positive was positive, I counted as positive. When negative was negative, I counted it as negative. I move forward, I move backward, and I just want to see my net change from 0 to 2 for my velocity. And again, there's not much new on this one in terms of calculator tips. So -3 plus math 9 from 0 to 2. We'll go a little faster on this one. There it is. And we really didn't have much of a displacement, about 0.005 displacement. So we're at -2.995. That is our position. Okay. Is the particle speeding up or slowing down at t equals 1.5? Justify your answer. Okay. Our particle will be speeding up if velocity and acceleration have the same sign. They will be slowing down if velocity and acceleration have different signs. So here's a couple things we need. We need to know the velocity at 1.5, and we need to know the acceleration at 1.5. And just from a grading of the AP test point of view, we can't just put a of 1.5. We need to know that, we need to demonstrate our knowledge that the derivative of velocity is the acceleration. If you don't put a of 1.5, that's fine, but we just defined a to be the derivative of velocity. Don't just put a, you need to show that it's a derivative. So we need to find the derivative at 1.5. I'm sorry, we need to find the velocity at 1.5 and then the derivative of that at 1.5, and then we'll compare some signs. So let's clear our screen here. We have a couple ways of doing this. We could go to the table, and I'm going to do that first. What I always like to keep my calculator set on, in addition to radians, of course, in calculus class, what I like to keep my calculator set on is where I press second and window, and I personally like my independent variable to be on ask. That's just the way I like to do it. That way when I go to the table, I can type whatever I want, like 1.5, and I get 0.0253. 0.025, we'll leave it there. And really all I care about within the context of this problem is that my velocity is positive. Okay, another way of doing it is this. I'm gonna quit, second and quit. It's like an escape key. You could press alpha trace, pull up Y1, and then parenthesis, just like a function. This is gonna be like f of 1.5. It's the same idea, and it gives us that. And we can see more decimals this way, but there it is. Actually, we could see all those decimals if we go back to the table. Let's go back up. If you scroll around, you're sitting on that, see all those? Actually, we see even more there. So yeah, kind of neat, isn't it? Now let's find the derivative at 1.5. So let's quit. I want to know the derivative of the velocity at 1.5. The function I have is velocity. So we're going to do another little cool calculator trick. We're going to press math, and we need n deriv. And we're going to take the derivative with respect to, okay, it would be t on paper, but in our calculator it's x. So the derivative with respect to x of y1, so alpha trace, y1, at x equals, well, 1.5. And we get negative. Negative what? Well, it doesn't really matter. I'm going to write it anyway, but it doesn't matter because that is negative. And so we will justify our answer. Our particle, the particle, I don't know whose it is, but the particle is slowing down because velocity and acceleration have different signs at t equals 1.5. There we go. Because one of them was positive, the other one was negative, it's slowing down. It would be speeding up otherwise. Okay. At what value of t does the particle have an acceleration of 0.2 on the interval from 0 to 1? Okay, a couple things going on here. We're going to need the acceleration, and I know you're like, oh, we just did that. Well, actually, we found the acceleration at a specific point. Now we're going to need to just see the acceleration. Now, you're probably thinking, okay, great. I'll take the derivative of this. I hear you. It's doable. It's great. But this is calculator active. Therefore, let's not do the product rule with a chain here and a chain here. Just don't. I want to know where my acceleration, and actually at this point I could just call it A. We've defined it that way. I'm not, but I want to know where my acceleration, I'm just kind of redefining it here, is equal to 0.2. I'm going to graph that, but I'm going to graph it on this window. So let's jump in here. All right, we have y1. It's stored in there, it's saved, it is the velocity. I would like to graph the acceleration without ever finding the derivative. So let's do it. Math 8. Okay? So I'm taking the derivative of y1 with respect to x. So with respect to x of y1, so alpha trace y1, at what x value? At every x value. At any given x value, I want to have that derivative. So x equals, and this is going to sound a little redundant, but x equals x here. It's not at 1.5, it's not at 0. It's at 1.5 and at 0 and at the square root of 2. It's everywhere. Well, not everywhere. It's actually just from 0 to 1. But at any given x value, that's where I want it to be. So here's your function. Here's your derivative, and we're going to graph it from 0 to 1. Before we graph it, actually, I want to see where y2, which, by the way, is red on mine, equals 0.2. So I'm going to put 0.2. You can leave that 0 off, of course. And I said this is red, but let's not complicate things. I'm only asked about the acceleration, which is y2. I don't need y1. We can go up to y1 and go back to the equal sign and press enter. And now that equal sign is turned off. And then when we graph, the only graphs we'll see are y2 and y3. So let's do it. I want to graph from 0 to 1 though. So window, from 0 to 1. What y values? I don't know, and I don't have enough time to calculate that. The calculator will do it for me. Press zoom. You know where I'm going here. We're going to go to zoom 0. I'm not even going to scroll this time. It's zoom fit, adjust the y values given the x values that you've put in. And it's going to take it a minute, but we're going to have to find where these two graphs intersect. Here's one of the graphs. What you see horizontally is the x-axis. And it is graphing the derivative basically point by point. So that's why it's going so slowly. So we're just going to have to sit here and make small talk while this happens. On a timed test, I do recommend that if you want to move on to another thing that you're writing or doing while this is graphing, it's good use of your time. Okay, we want to know where acceleration equals 0.2. I want to know where that is, so let's find it. This is an intersection at this point, so second in calc, I'm looking for a point of intersection. So go to number 5. Well, first curve, my first curve is indeed red. My second curve is indeed the black one. If I had more than one curve in there, like if I would have turned on the original graph, the velocity, I would have had to move up or down to select the curves that I need. Okay, guess it just needs a starting point based on the way it calculates things. And there it is. It took it a second, but it is 0.7797. So I would love to write all this out and do all kinds of solving. No, ain't nobody want to do that. Bad grammar, but there it is. So 0.779, we're going to round that up. So 0.780, we'll round it up there. And there we go.